is Ramin Yarmohammadian, and today I'm presenting two-stage mechanism for fire-induced spalling in concrete, which is part of my PhD thesis in Politecnico di Milan, supervised by Roberto Felicetti. So starting with the definition of spalling. Spalling is a cross-section reduction with a possible violent projection of particles, and in the literature you can mainly find two main mechanisms. The first mechanism is a thermal stress mechanism, in which they think a mechanical effect of hot skin or buckling of hot skin will create spalling. And the second mechanism is pore pressure, in which when the pore pressure exceeds a threshold which is connected to the resistance of concrete, the spalling can occur. But unfortunately, none of those mechanisms can explain the event fully. So a new mechanism which is based on a combination of these two can help us understanding the mechanism then. So in my PhD, I also presented a two-stage mechanism in which we distinguish two phases or two stages in the whole event: crack initiation, which is followed by crack instability. And this idea is inspired from many stable cracks that are found in a post-fire assessment of structures. In fact, having a stable crack can help us from a structural point of view, in which that crack can help as a thermal barrier to stop the flux or thermal energy which are going inside the inner part of the concrete, which is the core part of the cross-section usually. So in this presentation, what you will see is first you will see what is the resisting force against spalling. Then you will see what are the main contribution in the first stage, or how is the crack generated. And then you will see how does the crack get unstable, which is connected to the second stage. So for the resisting force in spalling, I would say the only resisting force against spalling is the fracture behavior of concrete. How do we need to get it? Also, I presented a new test setup in which you can characterize the fracture behavior of your concrete using new direct tensile tests, which cancel out the secondary bending inside the concrete. So as you see here, the difference between the normal concrete and high performance concrete is not just the strength, it's not just the increasing branch, it is also related to the decreasing branch or the falling branch after the peak. So in the first stage of spalling, we need to reach to the strength or to the peak of the material itself, and which is different in the normal concrete and high performance concrete. The question is, how do we need to reach there? So starting with one literature there is research already, which was in 2019, in which they splitted concrete cubes while heating from two sides and while measuring the pore pressure in the fracturing plane. And then they got to the conclusion that the pore pressure alone cannot fracture. So pore pressure can reduce the tensile strength, but cannot fracture alone. And this connection between the pore pressure and reduction of tensile strength is dependent on how pores are distributed in the fracturing plane, or how pores or damage are connected with each other. For example, in this case, if we have high performance concrete, there are less pores, so the pore pressure is not as effective as it is in normal grade concrete. So in the normal grade concrete, since we have high number of pores or damage, so there is more area in which the pore pressure can effectively work there. So the bio number in which it connects the pore pressure with the effective reduction in the tensile strength is depending on the pores. But the question is, so if the pore pressure alone cannot overcome the tensile strength, so how we can reach there? And the answer is usually we need to combine it with the thermal stress. So for small scale tests, I've done some tests to understand how we can combine these two with each other. So we had high performance concrete or ultra high performance concrete with different heating rates in a small scale, like cylinders, as you see here. And then I used a numerical analysis to know what is the temperature and stress at the time of spalling or at the time of explosion. And then by having thermal analysis, I have the temperature at the moment of spalling, and assuming the upper bound of saturation pressure at the moment of spalling, I can get effective pore pressure inside the samples. And then by combining to thermal stress at the middle, considering the transient creep, we can get something which is like a threshold for each material. So the combination of the pore pressure or effective pore pressure and tensile stress for each different concrete can reach to almost a same or a threshold in which the concrete explodes. And if we go faster, so if the heating rate is higher, so the share of the thermal stress prevails through the effective pore pressure. And then if we go slower, the pore pressure part is prevailing at the end. So the question is, if it is so easy to just combine thermal stress with the pore pressure, why don't we do it in the normal cases? And the answer is, unfortunately, in normal cases, we do not have such easy way of combination of pore pressure and thermal stress. In the normal ways, in the normal structure, we usually have a wall which is heated on a side. So we have 1D heat transfer, let's say, and then this produces biaxial compression. And this biaxial compression is not in the same direction as instability. And then this value is usually high, like in a fully restrained material, this can reach to even 60% of compressive strength. And then how we can combine this biaxial compression and on one direction to the instability on the other direction. So the answer might be here. So if we push concrete on one direction, we will reduce the tensile strength on an instability direction. So as for example, if we go 60% biaxial compression, the tensile strength on the other direction will reduce to 30%. And this 30% can be reached by pore pressure or effective pore pressure. So this is usually the combination that we find in the normal or in the reality. So that can be also helpful for the future large scale tests. So in the second stage, by the way, we need to know if we just have thermal stress, what's going to happen. So as I said, the concrete needs to be fractured and needs to accelerate the particles. If we sum these two with each other in a 1x1 concrete cube, we need almost 2.5 kilojoule per square meter energy. And then how much energy do we have from a thermal stress is in the whole concrete cover. So in 20 millimeter of whole concrete cover, we have just 1 kilojoule per square meter energy which is stored there. So obviously this 1 kilojoule per square meter cannot give us enough energy for accelerating particles, so we need alternative source, and this alternative source in concrete at high temperature is thermal energy. So in each second at high temperature we have between 25 to 50 kilojoule entering the cross section, but the question is how you convert thermal energy to the mechanical work, and the answer in this case is water evaporation. So how? Concrete is like a sponge, as you see here, and this sponge at high temperature is heated, and with 90% of mass which is heated, and then this 90% can give instantly their energy to the pores where we have water there. And if we imagine just 3% of water which is vaporized in this process, we're gonna have 4 kilojoule per square meter, which is enough for the spalling. So in conclusion, we just really need very superficial layer of concrete which is engaging in water evaporation or this conversion from thermal energy to the mechanical work. This is also confirmed by neutron radiography test at ILL, in which we heated the concrete on the right side and we had a gap, a sealed gap on the left side. When we heated, this sealed gap got pressurized, and then we opened the valve, and by our command we were checking how much concrete is engaged in this vaporization of water. And as you see, it's just 1 millimeter of concrete, and the process is so fast, like in 0.03 seconds we have already a gradient which is happening inside concrete. So the next step would be how we can see it in a real life, because here it is a sealed gap. We wanted to crack a concrete and then to see how a real crack in a concrete acts in instability. So what we did is we insert a material inside the concrete while batching, in which it has higher thermal expansion. In this case is PTFE rings, and then this PTFE ring will heat it up like the other material, surrounding material, and then expands more. By higher thermal expansion, the crack creates in middle of the cylinders, and then we can have the instability depending on the parameters that we have there in the concrete. So as you see, this is the first test, spalling test that we could get it. Then we installed photosensors to see what is the displacement of each splinters. Taking the second derivative of that displacement, we could understand what is the acceleration, and from the acceleration we can investigate the pressure inside the crack. And out of the test we could conclude that the pressure in which the acceleration comes through it is very close to the saturation pressure at that temperature in concrete. So in conclusion, we have 2 stages. The first stage, we need a combination of pore pressure and thermal stressor, which can combine with each other. In a small scale test, it is rather easy because the instability and the stress and the pore pressure, they are all in the same direction. So we can easily combine them with each other. But for the larger scale test, there is a combination of biaxial compression with the pore pressure, which are in the different directions. In a second stage, the pore pressure is leading parameter. So if we have water there, if we have thermal energy there, we can have unstable crack. So flash vaporization, in which we call a very short layer of concrete vaporizing the water very fast, helps in instability. And then it is also important to mention the post-peak behavior of concrete, or the falling branch after the peak is really important, because it's just the only resistive force there in the instability. So if we have a high performance concrete which loses its energy in very fast way, we lose all the strength or all the resistance very fast. That's why in high performance concrete we have higher risk of spalling than a normal concrete. And thank you for your attention. This was my presentation for the fire-induced spalling.